to mention is I realize that I'm an idiot. So you remember how I was all brilliant and got these EEPROM sockets? Well, put the EEPROM socket next to the EEPROM. Doesn't fit because I failed to measure and I got the single width, not the double width sockets. So the EEPROM sockets don't work because they're not the right width. Okay, so I'm going to order the correct ones this afternoon. That'll be double wide and will fit the EEPROM. Okay. So anyway, what that means then is for right this instant, two things. One, and let me get to the webcam. Okay, I need to put this here and switch to the webcam and video capture device, Logitech StreamCam. Okay, so what I was mentioning with the EEPROM is, let me get this correct. The EEPROM socket is this. The EEPROM doesn't fit. It's too wide. Okay, so I'll get the right part ordered along with some spares of some of these other chips just in case certain people fry certain chips. So what that means then is in order to leave as much room as possible for the socket, I put the RAM chip over on, which goes on this end, as far to one end as possible to leave as much room as I could for the EEPROM socket. So the width of it this way, or the length, I guess, should be roughly the same with the new sockets, but it may be slightly different. I'll have to double check the measurements. And so, but shove the RAM as far this way as possible to make sure that you've got plenty of room for the EEPROM socket. And in particular, when the arm is down, it will kind of bump one of the chips, but it's going to be, the chip is low enough that the arm being down shouldn't be a problem. Okay, so basically the EEPROM socket should fit just like where it does here, except it's going to be slightly wider when I get the right part. And so the other thing I would say is if you guys have already made your data wires and stuff, I would make them maybe slightly longer than they need to be because you can always trim a wire. You can't, extend it. But then also when you start plugging in things to the, let's see, where's my little pin? I need to get Ben has a really nice like pokey thing that he uses in his videos. I need a pokey thing. Huh? Okay. So, yeah, so roughly speaking, it should basically fit where you put the EEPROM socket, say a couple of spaces, sort of there. And just look on the inside to see, because where the pins are, right, the pins are kind of in the middle here. So you may have to kind of, keep track of where those are, because like I said, the new part is going to be roughly the same dimensions as this, except just wider. And so when you do your data lines that are running to the EEPROM, use the outside most row of holes so that there's room in the middle for the EEPROM socket to not be in the way of the wires. Okay, yeah.
So, you said like reminds me of those chips that you had.
Oh, yes. So, okay, so what are all of these? This is what is this chip? That's the processor. Yeah, the 65C02. Okay, so that's a processor. What will go into the EEPROM holder is the EEPROM, which is this chip. That's the one that says Atmel on it. Okay. And the EEPROM stands for electrically erasable electrically erasable and programmable read-only memory. Okay, so EEPROM, although people said EEPROM back in the day too, the original kind of this was not electrically erasable. It actually, there was a little window on the top of the chip, and you know how you erased it? Ultraviolet light. So you'd shine a black light on it, and that would erase the data. Okay. Later, we came out with EEPROMs, or electrically erasable, and there all you got to do is the programmer, an EEPROM programmer, could erase it just as easily as it could write data to it. Okay. So the EEPROM has, and I did want to start talking about that, 32K of memory. Okay, 32 kilobytes worth of stuff. That's only half of the address space of a 6502 processor, which can address up to 64K, right? So the way that we're going to map this memory into the address space is a little weird, but it makes sense because of the way the reset vectors and stuff work. Okay, so we're going to map this 32K of memory into the upper 32K of memory that the 6502 can address. Okay, now, how many bits do you need for 32K of memory? How many bits do you need to address that? Well, how many bits do you need to address the whole 64K? How many address lines do we have off our processor? Mm-hmm. So A0 through there's 40 pins on it, but how many of those are address pins? 16. So it goes 0 through 15, which means 16 total. Okay. All right. So that allows us to address 64 kilobytes or 64K worth of memory addresses, right? The chip only, or sorry, the EEPROM only has 32K. So we have to decide which 32K are we going to map the chip into, the upper 32K or the lower 32K. Okay, for the EEPROM, we actually want the upper on this one. Okay, and let me draw on a piece of paper here, and I'll kind of explain why. The EEPROM. No, that's the memory, or part. That's the read-only memory. The middle chip, yes. Okay, so this is kind of ghetto, but hey, it'll work. Because it's like I have an iPad where I could do this, but well, yeah, okay. So the problem is, well, I think maybe I've mentioned this before. If I ever struck it rich and like won the lottery or something, what would I do with all of that money? What would I do with my life? Yes, okay. I would hire a personal valet or butler or whatever you want to call them, and they would be responsible for keeping my office and my house in good order. Okay. So that would be on the list. The second thing is I would never fly coach again. Okay. I would always fly first class. And if I had like millions upon millions of spare dollars, you know how I've set up this table with all my crazy stuff? Forget it. I just build my own building on campus that would have my classroom that only I could use. And I would have like a personal administrative assistant and that would handle all of my emails and business. And then above my building that had my office and stuff would be my penthouse, and it would, where the butler would work, right? Um, huh? I've thought way too much about. Like, I even have floor plans in my brain as to what the my fancy office and stuff would look like. Of course, right? And actually, that's the other thing. So when I was a kid, and I think I was inspired by this because I played Clue a lot. Um, if I ever build my own house, there's going to be a secret passage. There has to be a secret passage. Like, yeah, there's got to be a secret passage. If I'm gonna have millions of dollars, I think I'm gonna have both. Like on one end it'll be the brick, and on the other end it'll be the magic bookshelf, or where you have to like pull the right book out of the bookshelf. Mhm. Hey, yeah, you'll just like there'll be a Commodore 64, and it'll be like program this, and then yeah. Okay, so anyway, the address space here. So we have on the processor, we can see 64K. Okay, so let me make sort of this diagram here. Okay, so this is our address space. Um, okay, there, right? That's our address space. And we're going to map the EEPROM into this upper half. Okay, and we're going to do that by using sort of two things. One is address line 15 will be select EEPROM, and address lines A0 through A14 will be the memory addresses. Okay, so give me a minute. Okay, so basically the upper half of memory, okay, all of those 32K addresses have A15 as a 1, right? And the lower half all have A15 as a 0, right? Because if you think about the address, right, let's say address FFFF would be this, right? That bit, the 15th bit, if that's a 1, then that means we're in the upper half of the memory address space, right? And if that bit's a 0, then we're in the lower half of the memory address space. Does that make sense? Okay, so anytime the address bus has a 1 on uh, in the 15th bit, that means that we're trying to work with the EEPROM, okay? Because that course, the address corresponds to something that's on the EEPROM. Okay, Cole, you don't look convinced. That's fine. Yeah. Okay. Good question. Yeah. So the far right hand one, the least significant bit is A0. Okay, and A15 is the most significant bit on the far left.
So like, is it going to read the first 15 and then it knows which one it's in, or is it going to read the first, and then, like the first? Like, why wouldn't it be A0 that it dedicates it?
Okay, so because A0, if A0 was dedicated, that would get us 32K of memory, okay, but every other byte would be in or not in the EEPROM, okay, because think about the far right bit, right? If you list out the addresses, so here I wrote all ones, right? What would be, if I wrote all ones and a 0 at the far right end, that would be something that would be not on the EEPROM if I tied the EEPROM to A0. And that's just too confusing, right? So by using the far left bit, the most significant bit, we make it so that it's the bottom 32K is nothing to do with the EEPROM, and the top 32K is the entire EEPROM. And it's not like layered, because that would be drive me crazy. I mean, we could, but like, there's no reason to do that. Okay, now here's where it gets a little bit irritating because the addresses on the EEPROM are not going to be exactly the same as the addresses that the processor accesses them at, okay? And so what I mean by that is if I address memory FFFF, this would be the address to the processor, okay? But on the EEPROM, it's actually going to be this. Which is 7FFF, okay? Now let's think about why that's the case. So grab the data sheet for the EEPROM, okay? So this is the one that says, this is the very last one, the one that says Atmel on it, okay? All right, so let's read the data sheet here. Yeah. Grab one of each of those. Huh? The one that says Atmel on it, because that's who makes the EEPROMs. Okay. All right, and it even says there at the right, 256K, 32K by 8. Yeah, ROM.
Oh, wrong.
ROM.
How many forests did you murder?
Huh?
How many forests did you murder?
Many forests.
This isn't enough to like actually cause physical damage if you hit somebody.
Yeah. Yes, don't tempt me. Okay. Okay, so the model number for this, right, is a 28C256. Okay, 28 refers to the number of pins, and 256 refers to the number of kilobits in this case. Okay, and it's 32K bytes because, of course, there's 8 bits in a byte. Okay. All right, so look at the pin configurations, which is on the very beginning of the first page. What do we see? There's only 15 address lines, not 16. Okay, and that makes sense because, well, for two reasons, right? It only has 32K of memory, so it only needs 15 address lines. If we had 16 address lines, we'd have 64K worth of memory. Okay, but that's not the kind of chip that we have. Okay. Now, there's also some chips here. Chip enable, output enable, write enable. There are how many data lines? 8. Okay, and that makes sense because we have an 8-bit machine. And then no connect and don't connect, you are just unused. Okay. And in this case, it doesn't look like we have the no connect or don't connect aren't on the yeah, okay. So then the diagrams that you see there, which one do we look at when we need to look at our chip? Okay, so there are four grid pictures there. Which one is the one that's relevant to us? Yeah, the rectangular one that's not square. Okay, so the bottom right. Okay, the flat pack or ceramic dip dual inline package. Yeah.
What would we need? Like, what's wrong with our breadboard and our setup to where we have to divide the EEPROM in half? Like, what different scenario would not require us to divide the EEPROM in half?
You mean to divide the memory address space in half?
Yeah.
Okay, so that would be if we had the full. So if I had a 64 kilobyte RAM chip. Well, okay, but that RAM chip's only 8 kilobytes. Okay, so that's the other. Okay, so there are two data sheets. Actually, let's look at that because we need to. Okay, look at the. There are two of them that say Hitachi. One of them is for the LCD. Okay, that's not the one we want to look at now. Look at the. Or I'm sorry, I think I said this wrong. The RAM chip. Okay, so the RAM chip here has how much data can it store? The Hitachi one, yeah. Yeah. You're looking at the right one? Yeah, not the LCD one, the other Hitachi one. Yeah. Okay. So 256 kilobits, organized as 32 kilo words, and a word is 8-bit. Okay, here. So our RAM chip also has 32K addresses, but we're only going to use 8K of them. Or sorry, I'm sorry, 16K of them. So I think I've wrote my yeah, sorry, I think I said 8K earlier. I meant 16K. So we're only actually going to use half of the RAM that's available on this chip. Okay. So if we wanted to have, right, if we wanted to have more memory, then, well, okay, to some extent we can't, right? Because what's the memory address space of our processor? 64K. That's it, right? That's literally it. And the only way you can get more memory than that is with bank switching, which is annoying. Okay. All right. So what we'll do is, let me go back to my little memory map here, right? Is, okay, so this, okay, is going to be our memory map. We'll have our EEPROM at the top that has 32K. Okay. We'll have our RAM at the bottom that has 16K. Now the RAM chip actually can do 32K, but we're only going to use 16K worth of it. Okay, which does seem a little wasteful. Well, right, because we'd run out of space basically. Okay, and then we don't really need to allocate all 16K for the I/O, but we will because we got so the input output stuff. So the screen and the fourth chip. So because what are the four big chips on here? You've got your processor, you've got your RAM, you've got your ROM. What's the fourth big chip? Okay, it's the other WDC chip. Well, it will interface with the LCD. Okay, so that's the 65C22 versatile interface adapter. Okay, which is the other Western Design Center sheet. Okay, okay. So that other chip will be when we send data to it, we'll be sending data to it and pretending that it is in memory in this address space, somewhere between 4000 and 7FFF. Okay, and so if I want to write to the screen, then I'll send data to a particular memory address that's somewhere in that range. Okay, and if I wanted to, for example, check whether or not buttons are pushed, or if I had a keyboard or something, I would map that into that range of addresses. Okay, good. Okay, so let's go back to the EEPROM for a moment. Okay, if I want to program data into address 8000, where do I actually put it in the EEPROM's address space? Okay, so we have two address spaces. We've got the EEPROM's address space and the computer's address space. Okay, so what is the EEPROM's address space? That's where it is relative to, for the processor. Okay, but internal to itself, so let me come up here. Okay, so it's like so. Okay, so the EEPROM's address space, because how many address lines are there on the EEPROM? 15. There's 16 on the processor, but only 15 on the EEPROM. Right, because it's only a 32K EEPROM. I mean, we could buy 64K EEPROMs. They do exist. Yeah, 2 to the 15th, which is 32K. Right, because 2 to the 16th is 64K. Okay, so this means that if I want the processor, when the processor tries to read data at address 8000, okay, it's actually going to be accessing address 0 on the EEPROM. Okay, and the 15th bit, the 15th pin, right? A15 on the processor is what tells me when A15 is active, when it's high, I'm trying to read from the EEPROM because that's what those address spaces are. And the other 14 tell me which address within the EEPROM I'm going and getting. Okay, so if I take, for example, 7FFFF, right, that is encodable with 15 bits, right? It should be 15 ones, okay? And if I add a 16th one at the end of it, then what does that turn into? FFFF, right? So what this means is that the addresses on the EEPROM are 8,000 lower than where the processor actually goes to get them. Okay, so it's kind of a relative addressing. Does that sort of make sense? You don't look convinced, Cole.
No, I'm trying to think. Wait, so on the ROM you're getting the bottom half?
The ROM is only the bottom half. There is no top half of the ROM.
So what happens when you read the other side of the
Ah, okay. There is no other side of the EEPROM chip, is what I'm saying.
smaller than oh, I see, because if you're reading the no, that makes sense.
Yeah, the EEPROM is only 32K, so there is no other half, right? What do you mean? Like whether or not I put it on the lower half or the upper half?
So you're just like cutting yourself off from half of the
It only has half of the addresses. Yeah. Okay. Why did, well, okay. For the ROM, it has to be the upper half. Okay. And there's a reason for that. Okay. What is the reason for that? Well, let's look at the data sheet for the 6502. Okay. Uh-huh. His many unborn children, yes. Okay, the 6502 data sheet, look at page 12. Yes. Sorry. No, that's not what the C stands for. No, because CO2 would be the letter O, not the number 0.
CO2. I don't know. I see an O. I don't know what you're talking about.
I think you need to get your eyes checked, Rippy.
Well, it's almost like I have glasses and terrible eyes anyway.
Yeah, well, okay. So, this is the reason why we had to put the ROM in the upper half. Well, one of the reasons we had to put the ROM in the upper half of the address space. Okay, so what are these vectors at the top? When you first fire on the processor, fire it up, okay, what it's going to do is it's going to look in memory addresses FFFC and FFFD, and the contents of data that it finds there, it's going to go to those memory addresses to then load in code. Okay, so what will we put in FFFC and FFFD? We will always put 8000. okay? And then the processor will say, okay, I'm supposed to start loading code from address 8000. Where is address 8000? Oh, it's over here on the EEPROM at address on the EEPROM of all zeros. Okay, so because the reset vectors are all in the top half of the memory map, we have to put our ROM that's going to have data in it to be executed in the top half of memory. So the reset vectors here are hard-coded to be those 6 memory addresses. Or, sorry, the memory, two of the reset vectors, and then the other are for the interrupts, which we'll deal with later. Okay? So that's reason number one why we needed to put the EEPROM, the ROM, and the upper half of the address space. Okay. The other reason is, well, okay, if I put the ROM at the upper half of the address space, where necessarily does the RAM have to go? In the lower half, because I can't put two things in the same place. Okay. Why is it that the RAM has to be at the lower half? Okay, is explained by, let's see. Okay, is explained by two things. Okay, look at page page 8. Okay, which tells us basically the registers setup here. Okay, all right. So when we were doing the things in ARM, we needed to have a stack pointer, right? Okay, what was the purpose of the stack pointer? Yeah, which, I mean, it sounds stupid to say that, but it's like, where are you in the stack, right? Okay, so the stack pointer, though, like, what was the purpose of having a stack at all? Why did we need a stack? Okay, either to save data that we need to use later, or what was, huh? No, not so much on the speed. For things like recursion, okay? Recursion here being an instance of a subroutine call, okay? So if I make a subroutine call, I have to know where I came from so that I can resume what I was doing before the subroutine call, okay? Well, in order to save where I was, I need to save that data somewhere. And the place that we did that was on the stack, right? We pushed the link register and the stack pointer, right? Those sorts of things. We pushed those onto the stack, and then every time right before we exited a subroutine, what did we do? We pulled them off the stack, and then we hit the ret, right? So you remember when we made subroutines, what was the very first instruction? STP x29 x30 stack pointer minus 16 exclamation mark. Okay, and then what was at the very end? LDP x29 x30 stack pointer 16, and then ret. Yeah. Okay. So on the ARM, when we were doing things in ARM, okay, what was the stack pointer's initial value when the program first started up? Well, we didn't really know in advance. Okay, a lot of times it was just, I mean, from our perspective, it was almost an arbitrary number. Okay, just wherever the OS gave us. Okay, now on the 6502, the stack pointer's starting value is 01FF, period. Okay, And so what that means is in the address space, the stack is all memory addresses that start with 0, 1. Okay, so how many such memory addresses are there? Goes from 0100 to 01FF. A little more than that. How about 256?
Oh,
Because there's 2 nibbles, right? Okay, so 256 bytes is the size of our stack at most. Okay, now, did our stack ever get bigger than that when we were doing stuff on ARM? It did, but only because how big were the values we were, like if I wanted to put data onto the stack, how big was that data? Like X29 and X30, how much data did that take? Well, how wide was X29? Yeah, how many bits did it take up? How big is X29 in terms of its data storage capacity? Yeah. How wide are all the registers? They're 64 bits, right? It's a 64-bit processor. The W's are 32-bit, right? So if I push, yeah.
Sorry, I thought you were talking about, like, not gonna lie, I did not realize you were talking about a specific register, because you just said X29. I was expecting like some, we've been going all these numbers with like processors, so I'm like, I have no idea.
Oh.
This very specific thing you're asking.
Yeah. Okay. So anytime we pushed a pair of registers onto the stack in ARM, we were pushing 16 bytes worth of data, right? So all it would take would be 16 subroutine calls for us to hit 256 bytes worth of stack, right? So when you guys wrote the Fibonacci program, for example, in ARM, the recursive one, did anybody ask it to do the 30th Fibonacci number?
It breaks because it doesn't have room on the stack.
No, on ARM it didn't break because the stack could be basically as big as you wanted. But on this thing it would, okay? Because the stack can only be 256 bytes, period. Okay. Now, that said, the amount every time we push every time we do a subroutine call, we're only going to be putting, I think, 3 bytes onto the stack. Okay. 2 bytes for the program counter and 1 byte for the status register. Actually, no, it's just 2 because we don't need to put the status register on for a subroutine. Okay, which means we could theoretically do a depth of 128 subroutine calls, right? Which is a lot, right? And more than we probably will need. Okay, so when they designed the 6502, right, while yes, it is irritating that the stack must be on page 1 of memory. Okay, and when I say page 1, what do I mean here? Okay, so yeah, there are 256 pages, 00 through FF. Each page can hold 256 bytes, 00 through FF. Okay, so 00FF is page, sorry, let me start over. 0000 through 00FF is page 0. And 0100 through 01FF is page 1. That's the stack, is page 1. Okay. Page 0 of memory is special because you kind of can treat it as if they're registers. Okay. So how many registers does our processor have on it? It looks like it just has 3, A, X, and Y, right? And A is the only one you can actually do arithmetic with. So in a sense, it's almost as if we only have 1 register, okay? But the 0th page of memory, you can almost treat as if they're registers in the sense that memory access to the 0th page is faster than to all other pages, okay? And so you can treat page 0 as if it's a giant bank of registers. Yeah, you just have to store it out to memory, okay? So writing to page 0 is faster than all other pages, yeah, by 1 cycle.
I think I asked this question earlier on the show.
No, not on this
Well,
processor.
no, like you're not moving it explicitly, but when you're actually doing it, it technically would be moving it to a register. It's not just immediately taking it from the data, like the memory address. It has to load it somewhere.
Yeah, the ALU has a data latch inside.
Yeah.
You just, so yeah, so Rippy's point is like, if I want to add two numbers in ARM, how would we do that? We'd have to load the first number into a register. We'd have to load the second number into a different register, and then we'd have to add them and put the answer into some register. Okay. You could put it back into one of the source registers if you wanted. Okay. On this guy, what we will do is you will always be adding either an immediate value or the contents of a memory address to what's already in the accumulator, and the answer always goes back to the accumulator. Okay, so that's different than what it was on ARM. Now, the reason that the designers of this processor did this, okay, is, I mean, this is a mid 70s processor design. Okay, in the mid 70s, doing silicon lithography was still very primitive technology. Okay, and the more registers you want to have on board the processor, the more transistors you have to pack into the processor. Well, more transistors on a processor makes it harder to fabricate and more expensive.
Is it a linear scaling or
I'm not actually sure. The transistor? What is a transistor? It's like a switch, right? It can be either on or off. And if you put just gajillions of these together, you get a processor,
Oh,
right? Put them together in the right way. I mean, yeah, okay. So there are, I think it's like 3,000 or so transistors on the 6502. That's it. It's kind of scary how few it is. Okay. But if we were to add registers, we would have to add transistors. Okay. But also all of our instruction set would get more complicated. Okay. So I think you'll see as we get into it why this is such a beautiful design because of how simple it is. Okay. And hence fast. Okay. All right. So the stack must be on page 0. And the stack is something we need to be able to write to, right? To put data on it. What did I just say? Oh, my bad. Okay, the stack's on page 1, yes. Okay, so the stack is on page 1, and the stack is something that we need to be able to both read and write to, correct? Therefore, the stack, if it's hard-coded to be on page 1, wherever we put our RAM had better cover page 1, or we're in big trouble, right? The stack's existence requires RAM. Okay, so this is why we're going to map our RAM chip into the lowest half of memory. Okay, because that's where the stack is, and the 0 page for that matter. Yes. Okay. Now, in our case, we're actually going to use the lowest quarter. We're only going to use half of the available space on our RAM chip. Okay. So we're wasting half the RAM chip, and that's okay. Now, if we were to buy, so I think the reason that he did this is because it's probably cheaper and easier to buy 32K RAM chips than it is 16K RAM chips nowadays, right? Now, back in the 70s or 80s, memory was incredibly expensive. Okay. And so, I mean, the Commodore 64 having 64K of memory available was like, wow, 640K ought to be enough for anybody. Yeah. That's somewhat apocryphal. 640K was the address space of the original IBM PC. And why 640 is a tale for another day. Okay. Okay. So that's going to be a little bit complicated when we program our EEPROM. Okay. So let me switch over here to two things. Okay. The Arduino, right? So here is the finished version of the Arduino code, and let me switch. Oops, not that one. Sorry. Okay, here is the finished version of the Arduino code that Ben writes through the course of that first video. Okay, you can download this from his website. The 6502 project has all the data sheets, all the schematics, all the part numbers, and all of his code. Okay, so anyway, what is this doing? Well, two things. He's defining here which lines, where are we going to connect our data and our address lines on the Arduino, okay? So 22, 24, 26, and so on, those are the pin numbers on the Arduino, not on the chip, on the computer, okay? And this is where your ribbony cables came in, okay, right? And what do you need for the ribbony cables? You need one bunch of 8, and that's for your data side. You need one bunch of 16, that's for your address side, Rippy.
In his video, I do not know if this was intentional or a mistake, but the first 8 are in a row, makes sense. The first 12, and the last 4
are on the other side.
Are on the other side. However, 3 of them are flipped like this, and the 4th one is here. If you look very carefully at the colors on there, it's not right. I mean,
okay. Well, he may have fixed it. Yeah.
This was flipped. Like there was 1, 2, 3, and then those 3 were flipped order.
Okay. Well, so how you tell to make sure you're not messing it up, right, is look at the data sheet, okay, and in our case, look at page 13 of the data sheet. Okay. Yeah, so he may have messed that up and then fixed it later and just didn't mention it. Okay. Well, okay. But for the purpose of the first video, it didn't really matter because all he was doing in the first video was just it looked random, right? Because what it was trying to do was it was trying to access memory, and he just wanted to show you that, like, hey, the memory addresses are changing. It's clearly trying to do something, right? It's only later when we put the EEPROM in that the memory is actually going to make sense, right? Because there's actually something to be read. Okay, so look at page 13 of the 65C02 data sheet, okay, where we've got the pin out for the processor. Okay, so Rippy's point here is that on address lines A12 through A15, they have to go in that order, right? Because that's how they're wired on the chip. Yeah. Make sure that your wires match that. Yeah, it's flipped on the video. Well, then he messed up. Yeah. Okay. Yeah. Okay. So, yeah. I mean, look, he's human just like the rest of us, right? And he's going to be able to say, why did I print out all these? Why did I murder an entire family of trees? Yes, because I'm a genocidal tree maniac. But no, I did it because we've got to pay attention to these data sheets, or we're going to screw things up. Okay, and fry 555 timers, for example.
Okay, not my fault. Putting it into a box where things get pushed together and then you plug it in.
It happens. Okay, it does happen. All right, so pay attention to the data sheet. Okay. All right, so let's get back to the EEPROM, or sorry, to the Arduino situation. Okay, so what we're going to do is there's going to be 25 things that get plugged in, actually 27, that get plugged into the Arduino. Okay, what are they? 16 of them are the address lines. Okay, 8 of them are the data lines. The clock, there's 2 more. And power. You don't. Okay, but so you don't have to power this thing with the barrel plug anymore. Okay. On the processor or on the Arduino?
I have 2 right here, and then I have
2. You do. Okay, I'm not sure what this one is then.
That's what it was in the video. So
okay. I'll have to look because I don't remember off the top of my head.
It's right next
What
to the
pin
last
is that one on the data sheet?
V7.
Oh, you just put one of the data lines on there. Okay. Where are the other data lines? These?
The data lines are on here. This.
Why did he put that data line on number 2? Oh, sorry. No. That's the read-write signal. Yeah. Okay. Yeah, sorry. So there, I forgot that one. Okay. So the processor, right, has a pin that tells us whether or not the process is writing to memory or reading from memory. Okay. And he's mapped them all in this particular way on the Arduino with those pin assignments. So the clock goes to pin 2, the read write is on pin 3, and then the address, those are the 16 spots, and the data lines are on those other 8 spots. Okay. So we've got those for certain. Okay. But we could also plug in the power and the ground to the Arduino, and the barrel plug, we no longer need that. Okay, because on the Arduino, the ground is there, right? Just find the ground pin. But where's the plus 5 volts?
It's right next to it.
It happens to be right next to it on the Arduino, which is nice. But where is it? How do you know which one it is?
It says 5 volts.
No, it doesn't.
Yes, it does. It literally says 5 volts.
No, it says VN.
What? I see 5V. Power.
Really?
Yes. You have a 3.3 and a 5V.
Oh, it does. Wait a minute.
Mine's the
VN would be.
mine's the cooler version.
Yeah, I'm sorry. I said this backwards. Yeah. So there's 2 ground pins. It doesn't matter which one you use, but you have the 5V up there. And so you can plug the 5V into the 5-volt rail on your breadboard and have the Arduino power everything rather than having to use the barrel plug.
So the 5 volts is not next to this ground. It goes from ground to ground. 5 volts.
Yeah, and I thought he meant the other side. So yeah, okay. Does that make sense? Yeah? Okay, so the barrel plugs are no longer needed, which is convenient. Okay, the Arduino can power the whole thing. Yeah, I'd go ahead and throw that in there. Right, remove the barrel plug, put it back in the box, and then get a red wire to go from plus 5 volts on the Arduino to, and a black one for ground, okay, so that you're set there. Okay, good. Now, I've loaded this code. I need to then upload it to the Arduino. Okay, so how do I do that? Okay, right. So when you plug the Arduino into your computer, most of the time this will automatically get detected, but not always. Okay. What you need to do is make sure that you select the board type is an Arduino or Mega 2560. Okay, that's the type of board that we're using. Okay, there are also, as you can see, tons of other Arduinos, and that have, are smaller or bigger and have different capabilities, but that's the one that we want. The processor is obviously, in our case, the Atmega 2560, okay? And then the port, okay, is going to, those of you who have Windows machines, this will look a little bit different. It'll probably be called like COM3, COM4, something like that. On on Mac or Linux, it's going to be /dev/something. And in this case, it's USB modem, and then you just got to pick the appropriate one, okay, to make sure that you're selecting the appropriate port to communicate with the Arduino. Okay, now that I have code, all I have to do is click this button here, and that will compile the code, upload it to the Arduino, and so it'll take a minute for that to happen. You'll see some blinkiness going on, okay, and then the Arduino will start doing its thing. Now, if I go to serial monitor, okay, I'm not seeing anything happening here. Now, there's 2 reasons for that. In the Arduino sketch, we need to pay attention to right here, this line where it says serial begin 5,000 or 50,000, 57,600. Okay. in the serial monitor, oops, that is not what I meant to do. Here, I need to change this down here to be 57600 baud. Okay, that basically is the speed at which the Arduino is transmitting data back to the computer. Okay, so every time in the program where it says serial or terminal write, basically, this data, all that's doing is dumping it to the terminal and sending it back to the computer for us to observe. Okay, but we need to be set at the same baud that it's being transmitted at, or else it's going to be garbage. Okay, does that make sense? No, because that's in the code. This is not. Because the program, well, for two reasons. One, at the moment, I don't have anything connected to the Arduino, so there's nothing to read. Okay, and the other reason is because what does he eventually do? He makes it so it only displays stuff to the console every time the clock pulses. Well, since I don't have anything connected to the Arduino at the moment, it's not reading anything, and hence it's not reading any clock pulses, and so it's not displaying anything. Okay, but if I were to plug this in to the board, then I would start to see stuff. Just short it. I could, right? I'm not going to short it. I'd go through a resistor to do that, but because I'm not a horrible person. Okay. Yeah, it does, right? But for example, okay, so let me actually just wire up some of this real quick. And if, shit. Okay, which pin did we put the clock on? Pin 2? Okay, so first let me get power and ground. Okay, so power, and let me get ground. Okay, so my clock is working. Let me change it to automatic mode. All right, which pin on the processor was the clock? Fourth one, pin 37, okay. And of course that's not long enough. Oh, well, let's see. Okay. And then the clock needs to be plugged into pin 2 on the Arduino. Okay, so now that I have the clock plugged in, so what am I seeing here? Okay, so what does all of this stuff mean? It's basically garbage, okay? Okay, but let's think about what each of these things are. So we have 16 bits at the beginning, followed by 8 bits. Those are our address and data buses. Now, right now, those numbers are basically garbage because I don't have anything plugged into the Arduino. Okay, so it's not actually reading those values. And then it has 20A0 and 40 at the back are the same things, just displayed in hex instead of binary. Okay, and then it's got R here because, well, I also don't have anything connected to the R pin. Okay, so what is the read-write pin on the processor? Which number was that? 3 on the Arduino and 34 on, okay, where's my data sheet? Okay. Read-write is, no, it's RWB pin 34. Okay, so that's 7 over. 1, 2, 3, 4, 5, 6, 7. Okay, and then that goes to pin 3 on the Arduino. Okay. Right. Well, okay, that may have been just when I was plugging it in, but the processor, right, is basically sort of stuck in a, because I'm not giving it valid data. It's reading in 40 as an instruction and then trying to execute it, but that's not actually a valid instruction. So it's just sort of no-opping, basically. Okay. So the processor is sort of hung, if you will. Okay, but if I were to hook up the rest of these data lines and address lines, okay, so let me just do that real quick. Not really. Shouldn't take too long. All right, let me get the data lines, and those are okay, 26 through 33, but 33 through 26 is actually the better way to say it, like you did, Cole, because which order they're in. Okay, where do these go on the Arduino? Where do the data lines go on the Arduino? 39 up. 39 up. All right, so I got all the data lines hooked up. Okay. Now, one thing to point out is you do not have to actually re-upload the program to the Arduino. So it stores whatever program you give it in memory, and when you power it off and then power back on, it starts the program you gave it, right? So you don't have to re-upload the Arduino code. But you do have to go to the serial monitor. Yes. Well, all right, where did my damn serial monitor go? Tools, serial monitor. Oh, it's just on the other screen. Okay. Sorry, I wanted it on this screen. Okay, so what is on our, oh, I'm sorry, I dragged it to the wrong screen. I'm sorry, guys. Yes, what would an excellent student do? Okay. Okay, so what are we seeing now? Yeah, we're seeing real things, okay, but sort of, but what's on my data line? No, it isn't. The data line is this one and then that one at the end in hex. Yeah, it's reading all ones basically. And that's because, well, I don't really have anything actually plugged into the data lines um, other than the Arduino, which is sensing what's there, but it's not actually putting data there, okay? And then my address bus is doing something, I'm not sure what, okay? Yeah, it looks like it's basically random, and that's because, right, what happens when the thing first fires up, right? So if I were to reset the processor, okay, what happens initially is it tries to, well, it does sort of 7 cycles of initialization stuff, but then the very first thing it's going to try to do is read from memory address FFFC and FFFD, which is where the reset vector is. Now, what is it going to find at those locations? Nothing, garbage, okay? And so it's not actually going to start actually executing anything at this moment because I'm not giving it any data to execute, okay? Now, if I put data on my EEPROM, okay, and then gave it to the processor and put, wired it in, then we'd be set. Now, I don't have it wired in at the moment, but that's where we need to go. Okay, so that's the Arduino side of this, and now let's talk the EEPROM part of this. Okay. Yeah, they may be different because it's basically treat the numbers as garbage for right now. Okay. Okay. So that's the Arduino part, but what was the other thing that we need to do? Okay, let's download his Python script here, or actually just look at it. Okay, so this here, okay, that's the reset vector. Okay, and where did he put the code so in his example, I mean, I don't have it all hooked up this way, but he has a blinking light, okay, eventually, right, like not at the end of the first program, but later, okay. So how do I write data to the EEPROM? Well, I need to do 2 things. First, I need to make a binary image that is 32K in size, okay, and so what he does is we're going to make a byte array and put some stuff in it, and then we're going to make sure that it has basically 32K, okay, worth of stuff. All right, so if I were to run this program, let me just download it real quick.
Again, the way that Python is doing that, is it just concatenating those 2 lists together?
Not quite, and I'll show you what I mean here in a second as to why. Okay, so let me get my terminal open. Okay, so what the program is going to do here is, so it's going to make a byte array by concatenating the code that's up above with however many EAs are necessary in order to fill out 32K. Okay, and then it's going to replace 2 of those things at the end at FFFC and FFFD, or sorry, 7. Yes, okay. Remember when I said that the memory address location for the processor and for the ROM are different? So earlier, where is memory address FFFC? That's where the processor goes to look, but where does it actually find that? At 7FFC on the EEPROM. Yeah, because what's the address space for the EEPROM? Is always a 1, right? But the 15th bit doesn't exist to the EEPROM. It only reads 14 bits. Or sorry, 15 bits 0 through 14. Okay, so so on the paper when I was laying out the memory, right? Where is when the processor tries to access memory address memory address FFFC, where does it actually get that? It's coming from the EEPROM at address 7FFC, right? That, yeah? Okay, so the reset vector on the EEPROM is 7FFC and D, but where does the processor get that? At FFFC and FFFD. Am I not making any sense here?
Well, I thought it was kind of all that. That's actually corresponds to.
Yeah. All right, we should pack up because and quit. Okay. All right, I will send you further instructions and we'll pick up next time.